Welcome, this is a worksheet based upon mathematical induction. So let's try to solve it out the question. So for the first mathematical induction, let us try to expand the statement. So the letter Sn equals to plug in 1 plus 2 plus 3 plus and so on should plus n should be equals to 1 upon 2 times n plus 1. This is a statement. Now for the first basis step means n equals to 1. Take the left hand side and n equals to 1. N equals to 1 is 1. Right hand side, plug in n equals to 1. So 1 upon 2 times 1 plus 1, which is again nothing but what? 1. So we see that left hand side equals to right hand side. So therefore, the statement is true for n equals to 1. So that should be the first basis step. Then assumption step. Assumption step, let us assume that it is true for n equals to k. So 1 plus 2 plus 3 plus and so on plus k equals to k times k plus 1 upon 2. Now we have to prove that it is true for n equals to k plus 1. So 1 plus, I take the left hand side, 1 plus 2 plus 3 plus and so on plus k plus 1. When I do this one, so we can do another way. Where is that? We can get it out. What should be our answer? Our answer should be plug in n equals to, what is this, k plus 1 over there. So my answer should be k plus 1 times k plus 1 divided by 2. This should be my answer. K plus 1 times k plus 2 divided by 2. So how do I get it out from there or from here? So if I'm adding up to k plus 1, my previous term would have been k. So now if it is still k, this goes under assumption. It can be replaced as k times k plus 1 divided by 2. Then plus k plus 1. Now I see that I require 2 in the denominator. So what is missing? Multiplying and dividing by 2. Then I take k plus 1 by 2 as common. So when I factorize k plus 1 upon 2, what am I left over with? K and plus 2. I think so. That's only going to be the answer. So we can write it out. By principle of mathematical induction, it is true for, what is he asking it out? For positive integer. It is true for n belongs to z plus. Coming to the second question. Now again, this series or the expand that one, summation Sn equals to 1 cube plus 2 cube plus 3 cube plus and so on till plus n cube equals to 1 upon 4 times n square times n plus 1 whole square. Now I am going to take left hand side, which is 1 cube, which is 1. Right hand side also plug in n equals to 1. 1 upon 4 times 1 square times 1 plus 1 is 2 square, which is equals to 1. So left hand side equals to right hand side. So therefore Sn is true for n equals to 1. Now we have to assume that it is true for n equals to k. So till k cube, I am going to substitute it as 1 upon 4 times k square times k plus 1 whole square. We have to prove that it is true for n equals to k plus 1. So till k plus 1 whole cube. So what should be my answer? Plug in k plus 1 in the right hand side formula also. So I write it out over there. 1 upon 4 times k plus 1 whole square times k plus 1 whole square. So my answer should be 1 upon 4 times k plus 1 whole square times k plus 2 whole square. This should be my answer. So I'm going to try to get that answer. So before k plus 1, there would have been k cube. The before term would have been k cube. Now this entire thing goes in under assumption. So what is that assumption becomes as 1 upon 4 times k square times k plus 1 whole square plus k plus 1 whole cube. Now 4 is missing, so multiply and divide by 4. What can I take common? K plus 1 whole square upon 4 can be taken common. What am I left over with? K square. And what am I left over with? 4 and 1 more, k plus 1. Now it becomes k plus 1 whole square upon 4 times k square plus 4k plus 4. We can see that clearly k plus 4 is nothing but what? K plus 2 whole square. So it has been already been proved. So that should be the easiest way of getting it out. So first of all, write it out what is the answer that you are looking for so that it will be easy for us to proceed further. Now question number 3. Write the series again. The series will be Sn, plug in n equals to 1, 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1, so on till n times n minus 1 should be equals to 1 upon 3 times n plus 1 times n minus 1. So which is 0 plus 2 plus 6 plus and so on plus n times n minus 1 equals to 1 upon 3 times n plus 1 times n minus 1. So after finding the series, we should plug in n equals to 1 in the left hand side. So which is nothing but what? 0. Now the right hand side also I plug in n equals to 1. So it becomes 1 upon 3 times 1 times 2 times 0, which is 0. So therefore left hand side equals to right hand side. Therefore the statement is true for n equals to 1. I am not writing all the steps. These all steps are being automatically understood. Now we assumption that the statement is true for n equals to k. So I'm going to write it as plus k times k minus 1 equals to 1 upon 3 times k plus 1 times k minus 1. I have to prove that it is true for n equals to k plus 1. So what does that become? 0 plus 2 plus 6 plus and so on plus plug in k plus 1 times k plus 1 minus 1. And what should be my answer? Write down below. That's the beauty of mathematical induction. You know what is your answer should be. 1 upon 3 times k plus 1 times k plus 1 plus 1 k plus 1 minus 1. So my answer should be looking as k plus 1 times k plus 2 times k. This should be my answer. So now we go back and take this left hand side. So before term would have been k times k minus 1. Now we do the assumption. This entire thing is our assumption, which is nothing but how much? 1 upon 3 times k plus 1 times k minus 1 plus again k plus 1 times k. Now 3 is missing. Multiply and divide by 3. Now take k plus 1 upon 3 common. What else is left over? One more k, and you can take k also as common. So what else is left over now? Once I take into k and k plus 1 upon 3, k minus 1 plus 3 times plus 3, because k plus 1 also gone, plus 3. So what does that becomes? This becomes k times k plus 1 times k plus 2 upon 3. That's going to be the answer. Coming to the part B, hence deduce that sigma r equals to 1 to 2n plus 1 r times r minus 1. Sigma r equals to 1 to 2n plus 1 r times r minus 1. So we have cleared that formula that sigma r equals to 1 to n r times r minus 1. Formula we have proved it as 1 upon 3 times n plus 1 times n minus 1. Now this formula is still n. Now but do I have to n plus 1. So what am I going to do it at? Plug in n plus 1 over there. So this was n minus 1 times n plus 1. So plug in n as 2n plus 1. So it becomes 2n plus 1, 2n plus 1 minus 1, and 2n plus 1 plus 1. So what does that becomes? 1 upon 3 times 2n plus 1 times 2n plus 2. So take 2 common. So it becomes 4n. 4n upon 3 times 2n plus 1 times n plus 1. This is going to be the answer for 3 part B. Now question number 4. Prove by induction n square times n plus 1 whole square. So first of all write the statement. Sn is plug in 1 times 3 minus 1 plus 2 times 6 minus 1, and so on till where? Till n times 3n minus 1 should be equals to what? N square times n plus 1. Now take n equals to 1 left hand side, so it becomes 2. Right hand side, plug in n equals to 1. 1 square times 1 plus 1 is 2, that equals to 2. So therefore the statement is true for n equals to 1. Now our assumption, 2 plus 2, this is 2 times 5, 10, and so on till k times 3k minus 1 equals to k square times k plus 1. Now I have to prove for it is true for n equals to k plus 1. So what does the equation becomes now? 2 plus, or statement becomes 2 plus and so on. Plug in k plus 1 over here. So k plus 1 times 3 times of k plus 1 minus 1 should be equals to, plug in k plus 1 on the right hand side. So my final answer should be k plus 1 whole square times k plus 1 plus 1. So it should be k plus 1 whole square times k plus 2. That should be my final answer. So 2 plus 10 plus and so on plus, this is k plus 1 times 3k plus 3 minus 1. So what would have been the previous term? The previous term would have been k times 3k minus 1. Now this undergoes entire assumption. What is this entire assumption? K square times k plus 1 plus k plus 1 times 3k plus 2. What can I take common? K plus 1 I can take common. So it becomes k square plus 3k plus 2. So now I can factorize it out. K plus 1 times k square plus 2k plus k plus 2. So it becomes k plus 1 times k bracket k plus 2 plus 1 bracket k plus 2. So which becomes k plus 1 times k plus 2 times k plus 1, which is going to be a required answer. So therefore, by principle of mathematical induction, it is true for n equals to positive integer. Don't forget to write the conclusion. Coming to part B, hence use the standard result to find the value of n for this one. So let's write it out. What is that? Sigma r equals to 1 to n and r cube equals to, what is it? 4 times of sigma r equals to 1, sigma r equals to 1 to n, r times 3r minus 1. This formula was 1 upon 4 n square times n plus 1 whole square. And this one 4 times, just now what we got it at answer as n square times n plus 1. Now we have to find the value of r, n. So n square gets cancels, 1 n plus 1, 1 n plus 1 gets cancels. So what am I left over with? N plus 1 upon 4 equals to 4. So n plus 1 equals to 16. So n equals to 15. That's going to be the answer. Question number 5. Now what is the statement first of all? Sn equals to 5a, 1 upon 2, r equals to 1, 1 upon 2 whole square and 1 upon 2 whole cube and so on till 1 upon 2 whole to the power of n equals to 1 minus 1 upon 2 power n. So I take the first LHS, left hand side n equals to 1, it is 1 upon 2, right hand side 1 minus 1 upon 2 power 1, which is 1 upon 2. So therefore the statement is true for n equals to 1. Now let us assume that the statement is true for n equals to k, 1 upon 2 whole cube plus and so on plus 1 upon 2 whole per k equals to 1 minus 1 upon 2 per k. Now I have to prove that it is true for n equals to k plus 1. So plug in k plus 1 in the left hand side. So it becomes 1 upon 2 whole per k plus 1. What should be my answer? Plug in k plus 1 in the right hand side. 1 minus 1 upon 2 per k plus 1 should be the answer. So before k plus 1, what should have been the term? Whole to the power of k should have been the term. So now this entire thing goes under assumption. What is that? 1 minus 1 upon 2 per k plus 1 upon 2 per k plus 1. So I have to prove it out. It is 1 minus 1 upon 2 per k plus 1. So what am I going to do? Multiplying and dividing by 2. So it becomes 1 minus 2 upon 2 per k plus 1 plus 1 upon 2 per k plus 1. So we can clearly see that negative 2 plus 1 is going to be negative 1 because the denominators are same. 1 upon 2 per k plus 1. That's only has to be proved it out. So very simple, just multiply and divide by 2 and make the denominator same. Then the numerators are negative 2 and 1. Negative 2 plus 1 is negative 1. So again, by conclusion, by principle of mathematical induction, it is going to be true. Coming to part B. What is part B? R times R factorial is n plus 1 whole factorial minus 1. Sigma. So write down that question. So what is that question? Let me write down the question. By part B, sigma r equals to 1 to n, r times r factorial equals to n plus 1 factorial minus 1. Then what is this statement? Sn. 1 times 1 factorial, 2 times 2 factorial, 3 times 3 factorial, and so on. N times n factorial equals to n plus 1 factorial minus 1. Now the left hand side is 1 factorial. 1 times 1 factorial 1. Right hand side 1 plus 1 factorial minus 1, which is 2 factorial minus 1, which is 1. Therefore the statement is true for n equals to 1. Now assumption: 1 times 1 factorial, 2 times 2 factorial, plus and so on, plus k times k factorial equals to k plus 1 factorial minus 1. So that was our assumption. Now we have to prove it out. What we have to prove it out? Plug in k equals to k plus 1 over there. So 1 times 1 factorial plus 2 times 2 factorial plus and so on, plus k plus 1 times k plus 1 factorial. And what it has to be proved as? It has to be proved as, plug in what is this, k plus 1 in the right hand side. So what does it become? K plus 1 factorial minus 1. So which has to be proved as k plus 2 factorial minus 1. Now what should I do? We shall do very slowly. So before term would have been k times k factorial. Now this entire thing goes under assumption. What is that? K plus 1 factorial minus 1. Plus what else is left over? The blue color one? K plus 1 times k plus 1 factorial. Now what am I going to do? In these two I take k plus 1 factorial common. What else is left over here? 1 and 1 more k plus 1. And this minus 1 continues to remain as it is. So what do I get it out? I get as k plus 1 factorial times k plus 2 minus 1. K plus 1 factorial times k plus 2 is nothing but what? K plus 2 factorial. Because we know 4 times 3 factorial is 4 factorial. 5 times 4 factorial will be 5 factorial. So any number I take 7 and one number less, 6 factorial will become 7 factorial. So based on k plus 2 times k plus 1 factorial will become k plus 2 factorial. That's question number 5. B. Now come to 5C. So by principle of mathematical induction, you can write it out the conclusion. So 5C, what is question number 5C? Let me write here. It is sigma r equals to 1 to n 4 upon r times r plus 2 should be equals to n times 3n plus 5 upon n plus 1 times n plus 2. So write the statement first. Sn equals to, or Sn 4 times 4 upon 1 plus 2 plus 4 upon 2 times 2 plus 2 plus 4 and so on, 4 upon n times n plus 2 equals to nothing but how much? N times 3n plus 5 divided by n plus 1 times n plus 2. Now take left hand side, n equals to 1. If I take left hand side n equals to 1, 4 upon 1 times 1 plus 2, which becomes 4 upon 3. What about right hand side? 1 times 3 plus 5 is 8, 1 plus 1 is 2, 1 plus 2 is 3, which is again 4 upon 3. So therefore the statement is true for n equals to 1. Now let us assume that the statement is true for n equals to k. So it becomes 4 upon 3 plus 4 upon 4 times 2 is 8 plus and so on, 4 upon n times n plus 2 should be equals to, instead of n it was k, right? So k times k plus 2 equals to k times 3k plus 5 divided by k plus 1 times k plus 2. This is our assumption. Now we have to prove that it is true for n equals to k plus 1. For proving that it is true for n equals to k plus 1, what you should be doing it out, plug in n equals to k plus 1 in the left hand side and plug in n equals to k plus 1 on the right hand side. I have to prove that it is true for n equals to k plus 1. So 4 upon 3 plus 4 upon 8 plus and so on, plug in k plus 1 over there. 4 upon k plus 1 times k plus 2 plus 1, which is k plus 3, should be equals to, plug in k plus 1 over here in the right hand side also. When I plug in k plus 1 on the right hand side, n equals to k plus 1, what should I be getting it out there? My answer should be k plus 1 times 3 times k plus 1 plus 5 divided by k plus 1 plus 1 and k plus 1 plus 2. So what should be my previous step? Bottom up approach is better for these kind of question. K plus 1 times 3k plus 3 plus 1 is plus 8 divided by k plus 2 times k plus 3. This should have been the previous step. Previous step again would have been, expand it out, 3k square plus 3k plus 8k is 11k plus 8 divided by k plus 2 times k plus 3. This would have been the previous step. I have to land up from here to here. So my previous term would have been, what would have been the previous term? Previous term would have been 4 times k times 4 upon k times k plus 2. This entire thing goes in assumption. What is that one? K times 3k plus 5 divided by k plus 1 times k plus 2 plus 4 upon k plus 1 times k plus 3. Now we have to make a common denominator. For that, multiply this one with k plus 3 and k plus 3, multiply this one with k plus 2 and k plus 2. Then we get a common denominator for both the fractions. What is the common denominator for both the fractions? It is k plus 1 times k plus 2 times k plus 3. What else is left over in the numerator now? 3 times k times 3k plus 5 times k plus 3 plus 4 times k plus 2. Now I have to simplify this one further and see that I have only k plus 2 times k plus 3 in the denominator. Means k plus 1 is getting cancelled. This k plus 1 term in the denominator is an extra that should be getting cancelled. And after getting cancelled, I should be able to left over with 3k square plus 11k plus 8. So what am I going to do it out is, I have k plus 1, so bottom up approach again I am going to do. So before term would have been 3k square plus 11k plus 8 divided by k plus 2 times k plus 3. So because k plus 1 is there in the top one, so I assume that k plus 1 should have been cancelled. Now further expand it out this one, it becomes k times 3k square plus 9k plus 5k plus 15 plus 4k plus 8 divided by k plus 1 times k plus 2 times k plus 3, k plus 1 times k plus 2 times k plus 3. So it becomes 3k cube plus 9 plus 5 is 14, 14k square plus 15k plus 4k plus 8 divided by k plus 1 times k plus 2 times k plus 3. So we can see that when I multiply k plus 1 with this one, I'm going to get it out in the same way. So we can factorize this one. So we can directly write it out, the numerator as k plus 1 times 3k square plus 11k plus 8 and divide by k plus 2 times k plus 3 times k plus 1. Then k plus 1 gets cancels. You get it out this one, then factorize it out. It should be k plus 1 times 3k plus 8. Then it can be written out in this way. So like these questions, what we can do it out is, we can do from bottom up approach so that our assumptions and calculations will match each other. So that should be the easiest way to do the question. Coming to question number 6, the box below shows a student attempts to prove this by induction. Identify the error. So let us see what is the error. The first step, he has proved that the left hand side equals to right hand side basis step is correct. Assumption step is correct. But the third step, inductive step, it has to be proved. That is also has been assumed. So the third step is going to be an error. The assumption step is wrong. So what you have to write it out in that one? The answer is the student has just stated, but he did not prove it. Just stated and not shown that the statement is true for n equals to k plus 1. It has to be proved, not just stating it. Give a counter example, that is an example used to prove that something is wrong to show that the original statement is not true. So we have to prove that the original statement is not true. For example, we take for n equals to 2. He has taken for n equals to 1. So let us take it out for n equals to 2. N equals to 2. So what does that becomes now? For sigma r equals to 1 to n, r whole square should be equals to sigma r equals to 1 to n, r square. So for the left hand side, it becomes 1 plus 2 whole square, which is nothing but what? 3 square, which is 9. For the right hand side, it becomes 1 square and 2 square, because it is r square. So square 1 plus square 2. So what does that becomes? 1 plus 4, which is 5, which is not equal. So therefore, it is not true for n equals to 2. Question number 7. Again, a student claims that this is a proof. Now identify the error in the proof. Now what is the error in the proof? There is no basis step. The first thing is nothing but what? There is no basis step. No, not completed. What he says not been completed? Not completed the basis step. Give a counter example to the original statement is not true. We have to prove that the original statement is not true. So in the left hand side, plug in n equals to 1. It becomes 1. In the right hand side, plug in n equals to 1, 1 upon 2 times 1 square plus 1 plus 1, which becomes 3 upon 2. So therefore the statement is not true for n equals to 1. That's going to be the answer. Now to the next question, which is a challenge question. Prove by induction. So first of all, what am I going to do? I am going to write the statement. The statement is plug in 1, minus 1 whole to the power of 1, 1 square, minus 1 whole to the power of 2, 2 square, and so on. It becomes minus 1 whole to the power of n, n square, equals to 1 upon 2 times negative 1 whole power n times n plus 1. Now we have to prove that it is true for n equals to 1. So left hand side, it becomes negative 1 whole to the power of 1 times 1 square, which is negative 1. Right hand side, 1 upon 2, negative 1 whole to the power of 1 times 1 plus 1, 2, which is again negative 1. So therefore the statement is true for n equals to 1. Now let us assume minus 1 whole to the power of 1 square, minus 1 whole to the power of 2 square, and so on. Minus 1 whole to the power of k square, equals to 1 upon 2 times minus 1 whole to the power of k times k plus 1. Now what we have to prove? That it is true for n equals to k plus 1. So plug in k plus 1 on the left hand side. 1 square plus minus 1 whole square times 2 square plus and so on. Minus 1 whole to the power of k plus 1 times k plus 1 whole square should be equals to, plug in k plus 1 in the right hand side also. My answer should be equals to 1 upon 2 times minus 1 whole to the power of k plus 1 times k plus 1 times k plus 1 plus 1. So what should be my answer as? I do bottom up approach again. Minus 1 whole to the power of k plus 1 times k plus 1 times k plus 2. This should be my answer. So before term, what would have been the before term? Minus 1 whole to the power of k times k square. This entire thing goes under assumption. What is that? Minus 1 whole to the power of assumption. It will become 1 upon 2 times minus 1 whole to the power of k times k plus 1 plus the pink color one, minus 1 whole to the power of k plus 1 times k plus 1 whole square. Now I have to get to that part. From this part, let us copy this part from here to here. I have to work from here to here. So what is missing over there? 2 is missing. So multiply and divide by 2. Then minus 1 whole to the power of k. So for this, I'll multiply and divide with minus 1. So these two will become minus 1 whole to the power of k plus 1. So I could able to get minus 1 whole to the power of k plus 1. I could able to get 2 also. Then I can take k plus 1 also common. So minus 1 whole to the power of k plus 1 upon 2 times k plus 1 as factor it out, common. So what is left over now? Minus 1 whole to the power of k plus 1 is gone, 2 is gone, k plus 1 is gone. So what is left over? K upon minus 1 is left over, so minus k. Then over here, 2 is gone, minus 1 whole power k plus 1 is gone, 1 k plus 1 is gone. So what is left over? 2 times k plus 1 is left over. So what does that becomes now? Minus 1 whole to the power of k plus 1 upon 2 times k plus 1 minus k plus 2k plus 2. Is it minus 2k plus 2 is nothing but what, k plus 2? Yes, it is going to be k plus 2. So that's all. We got it out, the answer. So by principle of mathematical induction, it's going to be proved. So don't forget to write the conclusion. So that completes this 8A exercise or one exercise where we have used mathematical induction to prove the summation series. So in the next one, we follow the next model of the mathematical induction. See you in the next video. Bye.